All right, so now we're going to take a look at a couple other examples of how we can calculate the equilibrium concentrations. So here we have an example. We're told that the Kc equilibrium constant for this reaction between hydrogen and iodine to produce hydrogen iodide. So H2 plus I2 to give Hi. And again, this equation, you always want to double check that it is balanced. Doesn't hurt to make sure that it is. We're told that the Kc for this is 54.3 at a particular temperature. Remember, equilibrium constant values, these always need to be defined at a particular temperature because it is temperature dependent. So then we're asked to calculate what will the concentrations be at equilibrium. Okay, so we need equilibrium concentrations. If we start with, so we're given now initial concentrations, 0.24 molar concentrations of both the H2 and the I2. So we're given initial concentration. So this then would imply if we need equilibrium concentrations, we have initial that we need to create an ice table. Okay, and we're going to use our equation to help us. So we have H2 plus I2 to give HI. All right, those are the products. So we have our initial, we have our change, and we have our equilibrium concentration. So that's our ice table, and we can write in these values. So initially, we're told that we have 0.24 molar of the H2 and the I2. Okay, so obviously, initially, we're not going to have any of the HI to begin with. The change that's happening, we can define as X, as relative to one of the reactants. So when we start with H2 and I2 and they get used up, we're going to lose a certain amount, which we'll define as minus X. And according to the stoichiometry of this balanced equation, if I lose minus X, or if I use up X of the H2, I'm also going to lose or use up X of the I2. Well, how is the HI going to be affected? Well, we're going to be generating HI, so we're going to gain. That'll be a positive value. And then how much are we going to gain? Well, again, according to the stoichiometry, we have a 1-to-2 ratio. Okay, so if I lose or if I use up X on the reactant side, I'm actually going to gain or generate 2X on the product side. All right, so the stoichiometry does come into play and we need to address that in our ice table. So now at the end, at equilibrium, what we're going to do is just substitute these now into our expression. So we have 0.240 minus X would be the amount or the concentration of the H2 at equilibrium. Same thing for the I2, it'll be 0.240 minus X. And then for the HI, well, it's 0 plus 2X, which will give us 2X, right, as our equilibrium concentrations. So once we have that defined, we can then go ahead and write out the expression. So Kc would be Hi concentration squared divided by H2 to the first power times I2 to the first power as well. We're going to substitute the equilibrium concentrations now into this expression. So Kc, so Hi is 2X, and that's squared, divided by 0.240 minus X times 0.240 minus X, right? Those are what we have in the denominator. And we can go ahead and simplify this now. Again, this eventually becomes a math problem, an algebra problem. So 2X squared would be 2X times 2X, which is 4X squared. And then in the denominator, when we evaluate that, we're going to get, so this is the same as saying 0.240 minus X squared. I'm actually going to leave the numerator as it is, not simplify it, and we'll see why in a second. So 2X squared, and then our Kc value was given as 54.3. Okay, so we know what that is. So what we can do now, so that's our Kc value. I'm just going to erase that. So we can go ahead, we can simplify this to solve for x. So if I want to get just x on one side, to simplify this, I can take the square root of the left side, the numerator and the denominator. And if I do that to the left side, I also need to take the square root of the right side. So what's the square root of 2x squared? Well, it is 2x. What's the square root of 0.240 minus x, all that squared? Well, the square root of that is also 0.240 minus x, and that's equal to the square root of 54.3, right? So we simplified it just using some basic math, some algebra skills. And here now we can rearrange our equation and we can solve for x. All right, so when we rearrange and we isolate x on one side, we have 2x is equal to the square root of 54.3 times 0.240 minus x. So 2x is equal to square root of 54.3 times 0.240 minus the square root of 54.3 x. Okay, so again, isolating x on one side, we have 2x plus the square root of 54.3 times x, and that's equal to whatever this is. We can evaluate that over here, and then we solve for x, isolate x on one side, move everything else over to the other side, and our x value there would be equal to 0.189. Okay, I didn't go through the remaining math here because I expect that you were able to do that. So we'll just say math it, using math as a verb. So we've determined what the x value is, or what value for x is. We can go ahead now and substitute this x value into our equilibrium concentrations and just simply determine now what these are. So the concentration, the equilibrium concentration of H2, which is the same as I2, would be equal to 0.240 minus x. Okay, and x there was 0.189. So that equilibrium concentration would be equal to 0.051 molar. Okay, so that's the concentration of H2 and also the concentration of I2. The concentration of HI at equilibrium is equal to 2x. So 2 times 0.189, right? And that would be equal to 0.378 molar. Okay, so again, we're doing a little bit of algebra to this. And just understanding what equilibrium is and setting up your ice table, that's really the only chemistry part of it. Everything else is actually math that we're doing. We're solving for x in this and also in the previous examples that we've looked at. So let's take a look at another example that's actually very similar to the one before because we're using the same equation. However, the strategy to solve this one is going to be slightly different. And this is a more encompassing strategy. It's a more complete strategy that you really want to employ in all of the examples, all of the situations where you have equilibrium systems. All right, so it says for the same reaction and temperature as the previous example, calculate the equilibrium concentrations of all three species if the starting concentration, so your initial concentrations, is what we're given, are as follows. So we're given H2, we're given I2, and then now we're also given HI. All right, so let's remind ourselves what that equation was. We had H2 reacting with I2 to produce 2HI. All right, and then we have our ice table. So if our initial, change, and then equilibrium, we can write these out. So initially, we're told that the H2 is what, 0.00623. The I2 is 0.00414, and then the HI is 0.0424 molar, right? These are all molar concentrations. So what we need to do initially here is we need to actually figure out, because now we're given in this problem the fact that not only are we starting with H2 and I2, we also have some HI present. So we need to determine, is this reaction, as we're starting with initially, is it going to proceed to the left or to the right, right? So will the reaction proceed to the left or to the right? In order to do that, we need to calculate, first of all, calculate the value for QC and then compare to Kc, the equilibrium constant, right? So we know when we write out the QC expression, it's HI squared over H2 times I2. So we can substitute those values into that expression. When we substitute them, right, we end up with 69.7 for the value for QC. And if we compare it to the value for Kc, the equilibrium constant, which we were given as, what was it, 54.3. Okay, so our Kc here is 54.3. So we compare these two. Okay, and what we see is that QC is greater than Kc. And according to what we mentioned previously, this reaction will proceed to the left, okay, or to the reactant side. So what that means is when we write our ICE table, the change now that is going to happen is as follows. Now the reaction is going to go in this direction as opposed to going from left to right. So we're going to actually now gain, we're going to increase the amount of the reactants. So we're simply going to add X. Again, we're going to define the change in terms of X. According to the stoichiometry, which is a 1-to-1 to 2 stoichiometry, if we gain X in H2, we're also going to gain X in I2. And the change in the HI now is we're going to use some of that up. How much are we going to use up? We're going to use up 2X. Okay, so note here, just because something is in the reactant or on the reactant side, it doesn't necessarily mean we're going to be using it up. We have to determine in which direction the reaction is going to proceed in the first place by comparing the reaction quotient QC to the equilibrium value Kc. So then at equilibrium now, we're going to have the overall value. So we're going to have 0.00623 plus X. That's going to be the amount, the concentration at equilibrium for the H2. For the I2, it is going to be 0.00414 plus X. And then for the HI, it is going to be 0.0424 minus 2X. Right, so these are our equilibrium values. We can then substitute those into the equilibrium expression. So again, we have our Kc being equal to HI squared over I2 times, oh, sorry, let's write it in order, H2 times I2. Okay, so we substitute these values into this expression. So we have our HI, so 0.0424 minus 2X, and that is squared, divided by H2, which is 0.00623 plus X times I2, which is 0.00414 plus X. Okay, so you'll notice now that the terms in the denominator are not identical like they were in the previous example. We need to actually evaluate this. So this is equal to, what was the Kc? 54.3. Okay, so now we have this entire thing that we need to rearrange and simplify. Okay, which again ends up being a math problem that we're doing. All right, so if we go ahead and multiply out and divide. So we end up with, if we rearrange this, we have 54.3 into 2.58 times 10 to the minus 5 plus 1.04 times 10 to the minus 2x plus x squared. Okay, so that's this entire thing that we have multiplied by the 54.3, and then that is equal to, if we evaluate the numerator now, expand that out, we have 1.80 times 10 to the minus 3 minus 1.70 times 10 to the minus 1 x, and then it's plus 4x squared. Okay, so yes, it looks a little bit more complicated, but we need to write it this way so that we can go ahead now and collect these terms that we have. So collecting like terms. Okay, so this should look familiar if you've taken any algebra class. We end up with 50.3 x squared plus 0.735x minus 4.00 times 10 to the minus 4, and that is equal to 0. So this part, I'm sorry, should look familiar because this is in the form of a quadratic equation. Remember, in a general quadratic equation, we have ax squared plus bx plus c is equal to 0. Okay, so a here is the 50.3, b is the 0.735, and then c, right, is this entire thing. So when you solve your quadratic equation, you solve it for x, if you recall, and this is in your appendix, by the way, in your textbook, if you forget. X is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. So we're going to substitute these values into the equation, the solution for the quadratic equation. So we end up with x being equal to negative 0.735 plus or minus the root of b squared. So b is the same thing, 0.735 squared minus 4a. So a is 50.3 times c, and c is 4.00 times 10 to the minus 4. And that's a negative value. Don't forget your signs, which is very easy to forget when you do this. Oops, that's divided by. See if I can make that line a little straighter. 2a, so 2 times 50.3. Okay, so you solve this for x, we end up with x being equal to, you get two solutions for the quadratic, because this is plus or minus here. We end up with x equal 5.25 times 10 to the minus 4, or x is equal to negative 0.0151, right? So we get two solutions for this quadratic equation. Remember now, x is a concentration, and x here and concentrations in general cannot be negative. So that means we can ignore the negative solution. So we're going to go with the first one, right? So our x value then is equal to 5.25 times 10 to the minus 4. We still have a couple more steps. We just solved for x. We need to go ahead and substitute that now back into our equation, our values, or the expressions that we have for the equilibrium values, right? So for H2, The H2 concentration will now be equal to 0.00623 plus x, and x here is equal to 5.25 times 10 to the minus 4. Okay, and that is going to give 0.00676. For I2, okay, it is equal to 0.00414 plus x. And x again is the same, 5.25 times 10 to the minus 4. Okay, and that's going to give us 0.00467. Okay, and these are all molar concentrations. And then for HI, concentration there is, what do we have? 0.0424 minus 2x. So 0.0424 minus 2 times 5.25 times 10 to the minus 4. And again, that concentration should be lower than what we started off. So that ends up being 0.0414 molar. Okay, so there are several steps involved, obviously. We need to figure out the equation that we're using, write down our initial concentrations, determine in which direction the reaction is going to proceed, to the left or to the right, and then assign and define x, or the change relative to x, or defined as x, sorry. And then depending on which direction the reaction is going to proceed, we're going to incorporate our signs. The signs are important, whether it's a positive or a negative. And based on that change, we can come up with the expression for the equilibrium, plug those expressions back into the expression for Kc, and then we solve for x, invoke what we know about quadratic equations if needed, and then we're going to take for the both solutions, the concentrations can't be negative, so we'll take the positive solution, substitute that back into our expressions for the equilibrium concentrations, and then calculate them accordingly. Okay, so again, when you do these problems, they really just boil down to math problems. In this case, we're doing quadratic equations, but they're stemming from a chemistry problem or a chemical problem, right? We're using the balanced equation again and stoichiometry, and writing the expressions based on the law of mass action.